Okay, our next guest speaker is Dr. Simon Goerger. He's a director at the U.S. Army Civil Engineering Corps. I was close, but he'll correct me. Dr. Goerger is also a member, an officer of the Society. He's part of our executive council, and he holds the office of Vice President for Professional Development. So part of Simon's responsibilities are to making sure the EPD happens and it runs. So he did a great job. He also leads our chair for communities of practice, for publications, and for continuing education. So he has a big role in the Society. He's on the board of directors. He's been on the board of directors for a while. And so without further ado, I'll let Dr. Simon Goerger introduce himself more, if you'd like, and provide his presentation. So thank you.
Thank you, Norm. Appreciate it very much. It's always great to have the president of the Society able to attend the events and introduce folks and be part of the whole entire organization. So thanks very much, Norm, for this opportunity and for introducing us this afternoon. Again, my name is Simon Goerger. I'm the director of the Institute for Systems Engineering Research out at Engineer Research and Development Center in Vicksburg, Mississippi. Lots of words. What does it mean? It means I do operations research and I lead folks that do systems engineering and operations research for the Army, focusing mostly on Corps of Engineer type events, which for the Department of the Army is actually quite extensive because we don't just do military systems engineering and operations research. We actually do engineering research for both the civil side of our government as well as for the military side of our government. Because we are the organization that's responsible for doing the infrastructure defense, especially the main waterways of the United States. So the Mississippi River, the Ohio River, major ports, things like that. We are also responsible for doing some of that engineering and research. We do engineering research that applies also to elements of force protection, like you heard from Dr. Brown. How do you protect buildings? How do you protect things like the Pentagon? So some of the work that our organization has done in the past is specifically the Pentagon, where the airplane hit back in November 2001. That was highly protected and just finished being remodeled based off of guidances that and processes that we developed down in Vicksburg, Mississippi. And due to that fact, that plane did not go through the first set of rings. Okay, if that had not been rebuilt at that point in time, that plane would have gone all the way through the first set of rings and been on the other side of the Pentagon before it would have even started to slow down. So those are the sorts of things that our organization does. Why am I giving you that background? Because it leads into some of the things that I'm going to give you this afternoon with regards to talking about some processes and implementation, a lot of the techniques and methodologies that you've been hearing about over the past 2 days. So I'm going to try to take you into some practical examples of that. What are we talking about? We're talking about big data. Why am I doing big data? Because we are changing inside the Department of Defense the way we're taking a look at acquisition for some of our major systems that we're looking at building. Inside the Department of Defense acquisition process today, anybody have an idea the minimum amount of time that it takes a major weapon system platform, take a look at an aircraft carrier or the F-35 or any other major system, anybody have a guess at how long it takes to get through the process from concept to deployment to the battlefield? 20 years, 18 to 22 to be specific, depending on the complexity of that system. For many of you, that's your entire military career. You start out as a lieutenant or an ensign in the design of some system, and it may show up on the battlefield as you're putting on 20 years and walking out the door. You may never ever see it on the battlefield. How do we get these systems out on the battlefield faster? Get better, more complete systems out on the battlefield so that we can go forward and build them. Well, basically what we do is we take a look at moving from what we call a point-based design to a set-based design. The Navy has been very, very good over the centuries developing their ships off a point-based design. They have a general concept of what they want a ship to do, and they take those general practices, those lessons learned from very sage shipbuilders over the decades, and they can take and iterate over that design over and over again as they come up with new concepts, new constraints, new limitations. Kind of sound familiar? Assumptions, constraints, limitations, something that you guys have been looking at over the past day or two. Problem is that every time you do that, it causes a total redesign of the entire platform. Okay, and that takes months. Versus a set-based design, if you can go forward and you can take a look at all possible variants of that platform, all different configurations of that system prior to setting the constraints and limitations, now you're throwing away potential options versus having to redesign new options. Okay, you're throwing away non-viable systems and maintaining all the viable systems you possibly can as far forward as you possibly can until you get to that point in time when you got to finally start bending those pieces of metal and building that piece of equipment. And that's what we're trying to go to today. What does that require? It requires big data, massive big data when you're talking to some of these platforms, and I'll give you some examples as we go forward. When you get that big data, what do you do with it? Well, you got to parse it, you got to look at it, you got to analyze it. And from my context, I look at it as a large trade space. And everybody comes to looking at a trade space from a different perspective. Depending on where you stand within inside your community of interest is going to depend on what you see as your trade space. If you're looking at a subsystem, you may be down on the bottom of this graph. If you're looking at a system such as a radio system or something like that, that has a few options but not necessarily tons of options, you may be as a subsystem level. Then you start getting up in the platform levels. Let's take a look at something like a Humvee or a truck. You're going to have a few more options there and you're going to need some more powerful tools. But then all of a sudden I'm taking a look at a family of systems, a family of trucks, a fleet of trucks that exists within a contextual operation of maybe logistics. And if I have a truck that sits inside of logistics, what does it have to do? It works as part of a team. What kind of a team? How about a team of fixed-wing aircraft that have to strategically move stuff from the continental United States into the theater of operations? How about a series of ships that have to move it across the ocean? How about a system of rotary-wing aircraft and fixed-wing aircraft to move things within a theater of operations so I can get them forward, so I can start putting them on hets and 5-ton trucks and HEMTs and all sorts of other things in order to move them up to the point where they're actually going to be used on the battlefield. That's a complete portfolio of systems. And I have to understand how my system is going to operate within that. I need a much bigger set of tools in order to be able to take a look at that. And they're all going to come in at different phases and times of operation because they all take different time in order to create. And there are existing systems that are out there today that I've got to integrate with. And I've got to take a look at it from the logistics point of view, the science and technology, how I'm going to develop this thing, how I'm going to buy this thing, and then how I'm going to operate and maintain this thing. And then I'm going to look at it by service, because every service has their own specific set of needs or requirements. The F-35, how many different systems do we have that are called the F-35? Okay. The Air Force has got a version. The Navy's got a version. Marine Corps wants a version. Everybody's got a different one because some are going to land on runways, some are going to land on aircraft carriers. I have to have specific service desires and needs as well. And I've got to look at it from my perspective as a manager. Am I looking at the short term, what I've got to build within my next tour, 2 to 3 years, over my career of 20 years, over the lifetime of the system? Take a look at the B-52 bomber. It's been out there for over 60 years. Over 60 years. Your grandparents weren't even born when that system was out there. Okay? So you take a look at all those different things, and all that stuff relies on one thing: a lot of data. Okay? A lot of real-world data that often gets placed in conduits or cylinders of excellence that sit within inside specific communities. But I need to have access that if I want to show that trade space to a major decision maker. Take a look at those 2- and 3-star SESs and general officers and admirals, those flag folks that are making those decisions. They are trying to make a decision across the spectrum of things, not just within inside a specific focus of one little niche. That's why they're strategic thinkers. They can't do that if I can't get access to this data as an analyst and show them their trade space based off of their perspective, whether they're the Lotus Edition, an operator, maintainer, acquisition guru. Where does that data come from? It comes from many places throughout the life cycle of a system. It may be historical data that I take a look at from the beginning in the upper left-hand corner of this slide. Or as I come up with some initial concepts, I start doing some basic modeling, some basic understanding of how the phenomenology of how this thing works. I might be able to do that on a desktop or a series of servers. As I move through the system, my system gets much more complicated. Not just in the complexity of the data, but the classification of the data as I look at more and more systems. So I may be having to move this stuff from a desktop machine over to high-performance computing machines in order to take a look at how I'm going to design something as complex as a ship. If I want to come up with literally tens of thousands to millions of variants of a ship using physics-based models just to look at its physics-based capabilities, let alone its operational effects-based capabilities. So I may have to move from different types of platforms, storing data at different volumes in different locations and analyze it in different ways throughout the entire process. But I'm still trying to look at trade spaces and figure out how to downsize, because how many admirals, generals, or SESs want to look at 100,000 variants or possible solutions? Zero, okay? They want to look at the best 4 to 5, maybe 10 at an outside chance. And that's what our job as analysts is, to take a look at those trade spaces, reduce them down into meaningful subsets so that we can present that information to our senior leaders, as Dr. Brown was talking about, in a meaningful manner, in a money slide, so that they can make their decisions quickly. Maybe 20 to 30 minutes is all you get with them. How can you convey the important aspects of the differences in the different systems that they're going to need to look in order to make their decisions? How are we going to do this? One of the ways we're doing it today is Department of Defense, Office of the Secretary of Defense specifically, has put out a program called Engineered Resilient Systems. The idea of this program is to take a look at the acquisition process and see how we can move forward in order to analyze data and move as much information and create as much data/information pre-milestone A. Milestone A, how many people here understand the acquisition process? I know that you're all so deeply ingrained in it. You've all received hours and hours of instruction of it as cadets and midshipmen or just standard students. The acquisition process is basically broken down into 3 major phases. Milestone A decisions, milestone B decisions, milestone C decisions. Milestone A decisions is when we come up with a general concept and we say, this is what the requirements are going to be. When you set the requirements for a platform system in the Department of Defense, on average, that happens at about the 5-year mark of a system. At that point in time, when you set those decisions based off the requirements and the analysts from the science and technology folks and some of the analytical folks at the different analytical organizations within the Department of Defense, those decisions that you make there today will determine 80% of the lifetime cost of that system. That's at about the 5-year mark. Okay. So that system that may survive for 40 to 50 years in the operational community, let alone another 15 years for the development side, is being made there. How do I take a look at that? How do I create that data? What sort of things do I need to bring in? This slide gives you an indication of all the different sorts of areas of data that we have to generate and create in order to bring in and try to move that as far to the left of the process as possible so we can create that set-based design versus a point-based design, so that the leaders have an opportunity to get the information they need to get their general ideas of where they want to go with that system at that milestone A decision. But we don't get rid of that data. We heard yesterday from the Admiral about the digital twin. There's a corollary to that called the digital thread. The digital thread is all this information that happens before you start creating that specific instance. That specific instance you track as a digital twin. All the data that comes up to that is the digital thread that helps support that. It's very important to maintain that data because as you go through the life cycle of a system, you want to make some life cycle upgrades. Having an indication based off of data that you've already generated in the past can allow you to quickly take a look at those modifications that you're proposing and see what the second and third order effects are on that system before you ever go back and tell the engineers to make those changes and start bending metal and putting in new communication systems or whatever else into your new platform or your modified platform. Spans the acquisition life cycle. ERS effort and the trade space analysis effort, trade-off analysis efforts that we're looking at through the large set-based design is going from beginning to end. I got to take a look at what is it going to take me to build it, what is it going to take me to analyze it, how am I going to take a look at putting that all together into a nice package from when I come to the concept all the way till I figure out how I'm going to decommission a system. Now, for many Army systems, that's not as big a deal, because a truck is not too difficult to decommission. I just take it to the shredder and chop it all up and take the spare parts and put it in something else. Decommissioning an aircraft carrier is a lot more complex, ladies and gentlemen. Trying to take a nuclear power plant and just say that I'm going to take it out and decommission it and go put it in the junkyard is not going to happen. What am I going to do with all that material, that nuclear material that I've been using over the years that saves me lots and lots of money when I'm operating it because I don't have to refuel as much, but costs me dearly when I have to dispose of it and figure out how I'm going to decommission that system. So we have to be able to track this information through the entire process. And that means it's going to transfer from person to person. specialty to specialty. You're part of a larger team when you're working in efforts like this. You should always be part of a larger team. Just like you were doing this week, a team that you may never have met before 2 days ago, but you sat down with, figured out the strengths and weaknesses of, analyzed the data together, and came up with some recommendations to senior leaders. Same sort of thing happens here. You may be passing it through 2 or 3 generations of analysts in order to be able to do that. This gives the components of the Engineered Resilient Systems program. I could go in excruciating detail and bore you guys more to death than you already are, but I'm going to just let you take a look at this. Realize, again, there are lots of components. You need lots of experts in this area in order to take a look at it. You need to be able to take a look at how I'm going to generate that data. What physics-based models am I going to use? What effects-based models am I going to use? And that's going to depend on how you take a look at what you want that system to be able to do. I want to be able to take a look and account everybody's perspective that I possibly can. I want that historical experience from actual operators to give me a full understanding of how that system could or should integrate with other things that are on the battlefield, because they're the ones who are going to have to operate it. How do I make that happen? And how do I follow through a specific process that is defendable and repeatable? Okay? I don't want to be able to just come up with an answer, create a great slide, and then the next person that comes in behind me can't understand it and can't regenerate that because it doesn't make any sense. It's not mathematically sound. It must be mathematically sound. That's what we get paid for, making sure that it is mathematically sound and defendable. Okay? That's part of what we get paid for. The big data challenge, the more data we generate, we're looking at Moore's Law on trying to help us out as much as possible. Okay? The pipelines get bigger, the processes get faster. I can do more on a desktop today. I can do more on my watch today than I could do on the computers I was using when I went to my master's degree program back in the 60s. How about back in 96? I'm not quite 60 plus years old. I was born in the 60s, but I didn't go to school in the 60s. Okay. So what we're trying to do is we're trying to take a look at how we move a lot of the analytical tools that we're using so that they can be operational on these other systems, these big data systems. If I generate it on a high-performance computing system and I'm storing it on a high-performance computing system, I want to do as much analytics on that system as I possibly can and then send the down-selected system down to my desktops and laptops where I can do further analysis, because is anybody going to take the HPC into the Pentagon in order to make show a decision maker what the answer is or a potential set of viable answers are? No. Is the network going to allow you to bring and connect into the HPC when you're in the Pentagon briefing the 2- and 3-star generals? No. So you got to be able to bring this down into a platform, a set of slides, some sort of mobile computing system that you can do that. Well, that means you have to down select and be able to transfer that stuff in a meaningful manner. Okay. The trade space tools that we're developing under ERS right now fall under a suite called Trade Studio, and there are 2 basic sets of tools. There's the Trade Builder, which helps us define and build the system, and the Trade Analyzer, which then helps us analyze the big data sets so that we can then pass that down to the other systems. Why are we running on HPC? Because we're starting to use more of these tools that have been created over the last 30 years. Ladies and gentlemen, these are physics-based models that the giants in these areas have been developing for years. Okay? They have been trying to put them together for us. There were standalone models. There were spreadsheet models at one point in time back in the 60s and 70s. They transitioned over to standalone models that were written in Fortran, and nowadays we're putting them in object-oriented programming and parallelizing them and running them on high-performance computing. This effort's been on for 15 years in order to place them on high-performance computing assets. We actually have 5 of them that are fully operational, the aviation systems, the meshing systems for geometry, so we see how thermal fluid dynamics actually work inside the computer system, so I don't have to build a whole bunch of wind tunnels and sea-based exploration of how water is going to flow over the fins of a ship or over the frame of a submarine. Radio frequencies, how is that affected by, again, the mesh, how my system is operating, where I put those antennas, and ship-based designs. The one that's currently is the most immature and under massive development right now is the ground vehicle designs. and that should be done within the next 2 to 3 years for initial operational capability. These systems all run on high-performance computing assets so that you can take them and actually run, instead of a point-based design, what we will see here in a minute, up to literally millions of variants, tens of millions of variants. Computational prototyping is one of the areas that we're moving into within the Department of Defense even more vigorously now than we have over the past years. We were trying to do this back in the 90s. I must have a timer on this because it keeps going off. But back in the 90s, we were trying to bring all these systems together, but we didn't have the computing power in order to be able to do it. Now we do. We have more of the computing power where we can start linking these high-fidelity models of the environment, high-fidelity models of the mission, high-fidelity physics models and simulations so that we can put them all together. We can generate basic information off of the physics-based models. We're working to transfer that information directly into missions operational models and bring in as much realistic terrain as we possibly can instead of geotypical terrain, geospecific terrain. How is this going to operate on the shores of the East Coast of the United States all the way to how it could potentially operate in the Middle East or China or Korea or wherever else we may need to be asked to take a look at how that platform is going to operate. So again, we can start taking a look at how resilient these platforms are going to be in actual environments throughout the world because we never know where we're going to have to fight in the next 10 to 15 years. I'll guarantee you right now when you could develop a concept 20 years ago where we were going to be fighting and operating, it isn't where we're fighting and operating today. So taking a look at that resiliency is key. These are 3 examples. This is the money slide. Everybody pull out your iPhone because I know you guys don't carry wallets anymore. You guys all have your credit cards on your phones. So take a picture of this. This is the one you're taking home for what you're trying to figure out today. These are 3 different examples of how we have taken and done, used efforts within inside of ERS to support different processes and different systems within the Department of Defense. So we have developed and helped the United States Navy take a look at different airframes as well as different ship systems. I have money slides for each one of these as well, but we don't have enough time for that, so I'm not going to give you a whole bunch of dollars. I'm just going to give you this one right here. For the Navy, we started out with helping them take a look at a set-based design for ships. We started out where they were developing 5 to 10 variants of a ship. And through using the high-performance create tools, going through numerous iterations with them, we actually developed over 22 million alternatives for the design of a basic littoral area ship. 22 million designs in less than 6 months. 22 million designs. That's a lot of designs, and obviously not all of those are viable designs, and all of those have to be assessed in some way, shape, or form, looking through the trade space analysis, okay, in order to find what system best meets the needs. How do I filter that down to that subset of systems that's going to be of value to provide information to the senior decision makers on which way they want to go. The Navy did that portion on their own behind closed doors because it became highly classified highly quickly, but we were able to help them at least generate what those alternatives would be. For the Army, we've done a couple different systems. We have taken a look at mid-life cycle upgrades of the CH-47, taking a look at how changing the different props on that system by taking a new material in order to develop a modified version of the prop, how that would change the lift and aerodynamics of that system. Oh, by the way, the second and third order VEX, how does that affect the transmission, the drive shaft, the power supply or power generation system on the side of that aircraft? Things that we couldn't do before, where we just basically were able to do some simple exploration of the blades and see what sort of lift we could have, and then we had to do a lot of real-time flight testing in order to see what was going to happen and how many transmissions we were going to burn out. Based off the modeling and simulation of high-performance computing, we were able to help set a series of graphs for them and help them figure out where they actually needed to test in order to see what the limits were of those different systems, which helped them more rapidly change out how they were going to make that midlife cycle upgrade. For the Air Force, we've been working with them on one of their programs, the LCAT, Low Cost Attritable Aircraft Technology. Basically, how are we going to potentially replace some of the UAS systems that they have today with either another UAS system or a comparable capability so that they could go out there and do reconnaissance. We actually do some of the Air Force cadets. We have Air Force Academy is working on that one with us as well. I should say some of the Army efforts that we've been doing under ERS. We actually work with the United States Military Academy, and we hope to, in the next year or two, as we work with a little more of some of the Navy stuff, is work with some of the Naval Academy cadets as well. This is a great opportunity to get people in on the front end of things and get them an opportunity to support some acquisition efforts. We also work with industry. Why? Because all this data has to be, we don't build these things, right? We give them to industry to build. But we have to be able to communicate to industry in a meaningful manner, give them the data that they need so they can actually come up with a specific design implementation. So we work quite heavily with them. As you see, we have Raytheon on here, Boeing, Lockheed Martin. We don't discriminate. We try to go out there and work with whoever needs to work with us in order to make sure that we can properly communicate the data back and forth to each other. These are still works under progress. Okay, there's a lot of proprietary information that needs to be held, personal information that needs to be maintained. So we're trying to do this as best we can, but we're working with them because they see it as a benefit to them as well. Instead of handing them a 500 to 1,000 page requirements document in Word, and then them having to translate that into something that are a model description of what they're going to actually have to build and interpret the terms that we're using inside that document, can we provide them electrons that actually do that faster for them so they can spend more of their time actually refining their designs versus having to interpret what we wanted as an initial platform capability. And then, of course, them being able to pass those designs back to us as easily as possible through electronic means so that we can take it back into our effects-based simulations so we can do our analysis of alternatives, which is another major analytical effort that operations research analysts do within the Department of Defense, to see how that thing is going to integrate, that proposed solution is going to integrate within inside the Department of Defense's current systems or planned systems for the future so that we can fight as one team. Here are some of those efforts that we're still going to be working on. These are some of the efforts that you, ladies and gentlemen, may be involved in over the next 5 to 10 years, depending on where you transition to after you graduate. Advances in infrastructure. That can be the network infrastructure. It could be the policies and infrastructure. There's a whole bunch of different things that we could be taking a look at there for infrastructure. Workflow automation. We are trying to make sure that we understand the workflow and influence the workflow appropriately. Okay? We don't necessarily need to use all the same people that we've been using for decades in order to do the same work. If we can take some of those folks who are retiring and replace them with some automation tools to pass on that information to the new analysts as they work and move forward. So what sort of things do we have to automate? A lot of the things that we've seen like on the physics-based models and the effects-based models, automating those things that used to take subject matter experts time to sit down and assess or generate and then assess versus just allowing them to take a look at what's being created and assess the appropriateness of those systems. Reduced ordered modeling, taking big data and make it something that's more applicable. Surrogate models, bringing that down into something that is appropriate representation of that real world phenomenon for the effort that we're trying to accomplish and the questions we're trying to answer. Cost modeling is huge. Cost modeling is huge. We have to understand what the real world costs are going to be, and not just for what the current phase of the operation that we're in, but the entire life cycle of the system. Doesn't do us any good to come up with a really great result or a viable response for today that's going to cost us 5 to 10 times more tomorrow. We're trying to make sure that we're not putting the Department of Defense and the nation into paying a bill that they can't afford in the long run. And of course, that cost modeling goes in with the effects-based modeling in order to help us understand, is this affordable? What bang am I getting for the buck, and am I willing to spend that money? Environmental simulation, environmental simulation, environmental simulation. The more that we do it, the more that we understand the different characteristics that we need to add into those models and simulations so that we can fully assess the different capabilities that we're trying to look at. Okay. At one point in time, all I need to know is how a vehicle is going to be able to travel across a piece of terrain. Could it go across that terrain or could it not go across that terrain? Go, no go. Pretty simplistic. Okay. Nowadays, we take soil cone density and atmospheric conditions and water solubility and everything just to figure out if this thing can drive across the field or not. Why? Because we're not always going to be staying on roads. So how are we going to be able to do this? And in the future, we may never ever use roads again. We may be using hovercrafts, but we have to be able to properly simulate that environment or model that environment in order to be able to do that. Okay, see if I can keep this thing from going forward. I'll probably kill it in the process. The summary slide. What are we doing? Okay, computational prototyping is necessary for us to do set-based design work. Okay, it is a must. We need to use the computers to help us generate tens of thousands to millions of alternatives in order for us to take advantage of big data type efforts. We can't generate that ourselves by just sitting down and running equations, okay? Taking our calculators and doing that. You guys are very comfortable with that. That's what we're trying to go through as we move forward and taking some other parts of the Department of Defense there. Engineered Resilient Systems is helping us move in that general direction by taking and moving a lot of these models and simulations over to systems that can generate that data, as well as building the tools that help us support the analysis of that data. Is it the end-all to be-all answer? No, but it's a step in the right direction. Science and technology challenges still remain in order for us to be able to accomplish that. Okay, the Engineered Resilient Systems program is on a 10-year timeline in order to get those tools in position in order to help reduce the amount of time that it takes to do other acquisition systems. So these are strategic efforts that we're looking at and we're trying to employ to make sure that we have the right tools for you all when you are in your mid-careers and for your students that you're going to be teaching, your people that you're going to be mentoring in the future, so that they've got the tools that they need when they come into position to have to do this work, to have to do this analysis, to have to make recommendations to senior leaders so they can have the knowledge that they need, so that they can have the understanding that they can need in order to make the right decisions for the nation and for our ability to do and live in the way of life that we're used to living in. So ladies and gentlemen, that pretty much concludes our presentation. This gives you just an indication of how complex a lot of these efforts are. This is not a one-shop type situation. We work across the spectrum, academia, industry, all the services. Okay. So do I have any questions at this time? Yes, Tom.
The computer models that you've now generated, how much are those used? How much are they used by, say, test and evaluation organizations where the testing is very expensive? And so now you've got real data, and you've got also data from your computer simulations. How much are people sort of synthesizing that data together to reduce test and evaluation costs?
Excellent question. So how many of these computer systems and the data that we're generating using these computer models being used by the test and evaluation community to reduce their overall number of tests, real world tests that they have to do? The CH-47 is a perfect example. We were able to reduce the number of, or I shouldn't say we didn't reduce the total number of tests that they did, but we focused their tests and we expanded what their overall knowledge set was, because instead of having to do a full run of tests in a short area, they were able to pick certain points along the curves that were able to be generated from those models and simulations to see, did the model properly represent, basically validating the model in simulation so that they could say that, yes, this data was viable for what we wanted to do. And then they were able to push the envelope. So they were doing their sensitivity analysis with their testing evaluation versus their discovery analysis with the testing evaluation. Harrison.
Thanks, Simon. So I'm gonna ask you a leadership question that sort of dovetails into Jerry's previous brief. As you push more and more of the development and testing into the computer, you're pulling it away from the physical world. And me as a helicopter pilot, I like to see vortex diagrams and blades chopping through air. So as you're pushing more of this away from the physical, do you encounter resistance from that? To that from decision makers, and how do you counter that and help to convince them that this is a good approach?
Another excellent question, because again, doing all the analysis and coming up with viable answers, if they're not going to be accepted by the leadership, don't do you any good. Okay, that's just a waste of time and a waste of money and creates a lot of frustration. So it's a lot of trust, and you have to build that trust over time. So it's not going back into your room and just working with the computers and creating all this data and doing all your analysis. You have to continuously interact with the leadership. Now, it's a little bit more difficult for the higher levels of leadership because you only can get in to see them, maybe once every 6 months, once every 12 months in an IPR. But with their staff officers, making sure that you're working with them, because they're the ones who are going to go back and brief the boss and saying, sir, ma'am, this is where they're going. These are the sorts of questions that they're providing answers to, and this is the level of fidelity. So they're helping to get the bosses comfortable with that sort of situation. Now, you also, in that context, you have to understand how that leader is going to be making their decision. What sort of way do they consume information? Do they like histograms, or do they like pie charts, or do they like spider charts, or they just want text? And you've got to be able to prepare your responses in that manner. So a lot of the things that we're working on, even with the big data aspects and analysis, is how to visualize that information. How do I get you as many different techniques to visualize it as possible so that it tells a story that properly represents what's really going on, not just leading them to your answer, but having them get contextual understanding of what's going on. Does that answer your question, Harrison? Yes, thank you. Okay, thank you. Colonel Cooley.
Thought I'd add on to Dr. Goerger's answer because we did some work with Iron Material Systems Analysis Activity in a similar type framework, not exactly ERS. And we were dealing with a simulation division that wanted to do full-on scenario runs. And we talked about this sort of, in silico set-based design. And what we were able to give them was, because of their resource constraints, they were able to manage a design of experiments on the order of about 12 different designs. Well, we can analyze 2,000 designs and give them better options for where they might allocate that 12 design space. So the people that still want to do hands-on testing, you're able to give them options that they otherwise wouldn't be able to test because they wouldn't even think about them. It's kind of another way to think about that.
And that brings up a lot of great points. Colonel Keeley talked about design of experiments. Just because you can generate 22 million, 30 million, 40 million designs doesn't mean you should, okay? You need to be able to make sure that you're developing designs in the right area, looking for the right answers, creating the right set of data so that you can analyze it appropriate. So again, that goes back to what we've been learning this week and doing this week. Understanding what the real questions are, okay, not what the boss came to you with, but making sure that you understand the situation enough that you understand the constraints and limitations. You develop a design of experiments so you're developing the right set of data to start with that you can do your analysis with. You don't want to do a bunch of analysis on worthless data. You want to do a bunch of analysis on the right data. Any other questions? Got a whole bunch of people on this side of the room that just feel like deep down inside they have a question inside of them, but for some reason they're just a little bit apprehensive of getting that hand up in the air. I tell you what, this is non-gradable, ladies and gentlemen, these questions, so don't worry about it. You're still going to graduate at the end of this year for all those who are seniors, and hopefully next year for those who are not. Please, are there any questions? Okay. Now, a lot of this is, becomes a lot more understandable the further you get down in your career. A lot of information that you got flooded with this week. I really appreciate the opportunity to be up here and speak with you today to give this sort of indication to y'all, some of the things that are going out there. This is just one program. This is just one set of examples of how operations research is being applied within the Department of Defense and within inside of industry, okay? It's a great community to be involved with. It's a great career to be involved with. I encourage you to take and can do continuous learning, because I tell you what, the things that we're doing today weren't even thought of when I was a cadet, okay? A lot of the stuff that you're going to be doing 5 to 10 years from now has not even come to fruition yet. That doesn't mean it hasn't necessarily been thought of, but the implementation of it hasn't been done. So do your research on how to do research and learn new things every single day, and you will continue to be a viable asset and a viable contributor to the Department of Defense, the nation, and the world for that matter. And Colonel Dabkowski.
Hello, sir. One quick question about the design space. As I was sitting here, it occurred to me, like you look at, let's say, 22 million different designs for a ship or something like that. Are you essentially bounding the possible design space a priori and then sampling without any learning from that space in some methodological way to generate those 22 million sample points? Or are you bounding in some sense early and then learning from what you're sampling inside of that space to lead you in a different direction for the combinations that you're looking at?
No, another great question. And again, as you take a look at, you can just do n factorial design and just create the entire space. What we actually did for the 22 million designs for the Navy is we started with a few of their seed sets and generated 22,000. Then we gave that data back to them. They analyzed it, they reduced it, and started focusing us in a specific area. And then we added more fidelity into that area. They went back and re-looked at those results, refined those again, and we started to get more tighter and tighter, higher fidelity every single time we did the iterations. We went through around 5 or 6 different iterations, increasing fidelity in certain spots. At first, we were trying to get the generalizable understanding of what was left or right so we could help define the box a little better. We wanted to have as much of the terrain map as we possibly could when we started with, but using those sorts of techniques and processes helped us to make sure that we were starting to develop more understanding in the really viable areas instead of just understanding all the non-viable areas as well. And that's just one process. Again, we're still learning on how to best do this. So, ladies and gentlemen, if you come up with some great techniques, we're willing to listen. If there are no other questions at this time, I'll pass it back to Norm,